6.7.
All right, so something about random variables and distributions and all that good stuff. We're just talking how sometimes she likes to make me look stupid, so I'll be the dumb sidekick this time, like I always do.
I don't like to make you look stupid, and you never look stupid. Okay.
Well,
A couple of learning objectives here. Represent the probability distribution for a discrete random variable. What the heck does that mean? And then also interpret a probability distribution. Also, what does that mean? So just jumping straight into our essential knowledge, the values of a random variable are the numerical outcomes of random behavior.
so any obvious that?
You know what, I kind of feel like, because in this particular slide, because it's the intro to something they've never done before, I really feel like I redefined everything. So we're actually going to jump the essential knowledge. So at the end of the video, you might want to come back to this point in the video, reread and make sure you got it.
Okay.
All right. So a random variable. You want to read it?
A random variable is a numerical value whose value depends on the outcome of a chance experiment. So if we do something, we're going to count the results, and they're going to be numerical rather than like blue or, oh, blue. Hey, look at that. If the random variable x is a number of heads we get from tossing 3 coins. So we're going to take a quarter and we're going to flip it 3 times and count how many heads we get. The end result could be 0, 1, 2, or 3. Okay, we couldn't get anything besides those 4 possible outcomes. I'm not going to get 1.5 heads. I'm not going to get 13 heads if I only flip the coin 3 times.
Right. And there's 2 types of random variables. The first is the one we talk about the most often, and it's discrete, which means we're going to count like we just did. But there's, the heads. But then there's also continuous. And so that's like when we talk about like the measure of something, like heights of females or something like that.
Yeah, we often report, like for example, temperatures. We report temperatures in whole degrees, but in reality, you know, it could be 48.7 degrees outside right now. Right. It sure feels like it's cold out right now.
It is chilly. Okay, so a discrete probability distribution. What does distribution mean, Mr. Bobby?
It's how things are spread out. So we're gonna, when we did the coin flips, going back to that one, I would want to figure out the probability of getting 0 heads, the probability of getting 1 heads, 2 or 3. So I could make a graph of those distributions of those probabilities is what we're talking about.
So given the values associated, the probability distribution does 4 things. It gives the values associated with each possible x value. So that wouldn't be a very interesting distribution, like 0, 1, 2, 3, right? Not super interesting. It is usually displayed in a table, but can be displayed in a histogram or a formula. And I'm going to try to show you an example of all of that. For every possible x value, the probability of x is going to be between 0 and 1. We talked about that before. Like, if you think about it in terms of like a percent chance, it'll make more sense that the probability would be between 0 and 100%, right? 0, it's never going to happen. 100%, it's always going to happen.
Well, it's never going to be more than one because nothing can happen with more than 100% certainty.
Right. And then for every value of x, what is this symbol again?
That's that weird funky looking E thing is sigma. It's summation. It means we're going to add up all the probabilities. So if I had a table for 0, 1, 2, and 3 heads, and I added up all those probabilities, they would have to total up to 1.
Right. Okay, so suppose you have some random variable x, and we're thinking about this idea of tossing 3 coins and recording the number of heads. Okay.
And I know she said, I'm sorry, I know she said this is kind of a boring thing, but this is actually kind of what we did with the Coke versus Pepsi lab. You could have gotten none of the cups right, 1 of the cups right, 2 cups right, or all 3 cups right. And we would like to figure out the probabilities each. Now that's a little slightly different, but that's the same kind of idea.
Yeah. So let's say we toss the 3 coins and record the number of heads. Your random variable x is the number of heads tossed. That's the random variable. That's the thing that we're measuring, right? The thing that's changing. If we want to create a probability distribution, then X can either be 0, 1, 2, or 3.
And then we'd need to calculate the probabilities of each one of those occurring.
Right. So what's the probability that I have 0 heads?
Are you asking me to tell you, or do you have
Yeah,
it down?
sure.
Okay, well, I mean, if you think about it, on the first coin toss, I would have the heads or tails. So if that means I would get tails on the first one, which is 50%, right? But then on the second one, I have to get another tail. So that's 50% times 50%, or 2.25. And if I did get 3 tails in a row, it'd be 1/2 times 1/2 times 1/2, which is 1/8, or 0.125. Okay.
Okay, I like it. So what happens if we try to find a probability of 1?
Well, that means of those 3, I'm going to get, I can get a heads in the first one and then 2 tails, or a tails in the heads in the middle and 2 tails, or a heads on the third or 2 tails and then a head. So there's 3 ways that could happen. And each of those probabilities would be 1/8, like I showed you before, or said before. So 1/8 times 3 would be 3/8, and that's 0.375. Yeah, 0.375. And that same one thing will happen for 2, and the same argument for 3, but backwards. Heads, heads, and heads would be 1/2 times 1/2 times 1/2, or 1/8.
Yeah. So you want to think
We
about.
kind of had this same conversation back in the Coke Pepsi lab. It really is kind of almost the Coke Pepsi lab.
Yep, it is. And you really want to think about ways it could happen. And I think that's where people get a little bit lost in the conversation, is like, oh, well, why isn't it 0.5 times 0.5 times 0.5 every single time? Because it's a 50-50 chance always. Well, it's the number of ways that thing could occur, right? There's only one way that you can get tails, tails, tails. And it's if it's tails, tails, tails. But there's 3 ways that you can get 1 heads, right? Like Mr. Bobby said, heads, tails, 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 heads, tails, or tails, tails, heads. And there's 3 ways that you could get 2 heads. Head, head, tails, head, tails, heads, tails, heads, heads.
I'm not going to write the other one out, but this is the one heads combinations. Heads, tails, tails. Yeah. And it would be the same thing, but they'd be reversed. So.
Yeah. And then there's only one way that you could get 3 heads on your coin toss, right? It'd be heads, heads, heads. So you have to think about like the number of ways that can occur.
And you could do this, and I think we're going to do it in another lesson, do a tree diagram, right? I could have made a tree diagram.
Yeah.
Of the tosses.
And then, of course, I can make a probability histogram, which is just some rectangles on a graph. You've seen this, like 0.125, 0.375, 0.375 for 0, 1, 2, 3, right? And this is a very generic one, but sometimes your probability distribution is given to you on the histogram. Okay, so suppose Nancy has classes 3 days a week. She attends classes 3 days a week 80% of the time, 2 days 15% of the time, 1 day 4% of the time, and no days 1% of the time. Suppose 1 week is randomly selected. So we want to think about first, what's the random variable? So random variable is X equals the number of days that Nancy.
Number of days Nancy lasts. I'm sorry, I'm laggy right now. Keep going.
Yeah, the number of days that she attends class per week. That's right. And then the second part says X takes on what values? So what are the values, the possible values of the number of days that Nancy attends class?
0, 1, 2, or 3.
That feels familiar.
Yeah.
Right? So suppose 1 week is randomly chosen. Construct a probability distribution table. The table should have 2 columns labeled X and P of X, what does the P of X column sum to? Okay, and I don't think, oh, I did do this. Okay, so maybe I should have waited.
Yeah, I could have drawn it, but all of it is given to you in the table in words or in percentages. So you would just match up each of the percentages with the appropriate day.
Right. In this particular problem, it's nice because the information is just presented to you as a percent, which is probability, right? So it's given. And then it says, what does P of X sum to?
And it better sum up to 1 or something's wrong. Now I've seen it where they've given you, like, they would give you 3 of the probabilities and you would have to figure out the 4th one, knowing that they have to add up to 1. So like we could have not provided you the 3-day a week probability, and you would have had to calculate that it would have been 1. So be prepared to work backwards as well.
Yeah. Okay. So I want to take the probability model and I want to create a histogram and then interpret the probability distribution. So you ready to create a histogram? I did not. Yeah, you're drawing this one.
Oh gosh. Okay. Well, you're going to make my life really hard because I'm going to try to draw 80 on one. So I'm going to go up here and say, I got to get my pen back. So this is going to be like 80 or 0.8. I'm just going to put 0.8. Okay. So when I have a bar way up here, that's going to be for 3. Okay. And I could have these touching, but I'm probably not going to right now. What was it? 15. So I'm going to have to estimate that 0.15. And these bars will be real fat.
Oh my gosh, guys, in a histogram, the bars are supposed to be the same.
I know, but okay, well, you're making my life miserable. I told you you make me feel stupid sometimes, but that's okay. All right.
Well, why did you start with 3?
I don't know, because I could draw 80% because I can't draw 1%. Okay. And then so 2 is going to be something like that. And I probably would push all these across the X. She's right. But now like 4 is going to be way down here. Okay. And I probably have my scaling off. That's what's really annoying me as a person who teaches, so this one's going to be like 4. Okay. And that bar right there would represent 1. And then 1% would be 0.01. And that bar is going to be like this. Okay, so this really she made it really hard for me to draw the scaling right now. I probably would have a ruler or technology if I really needed to be precise.
Yeah.
Or maybe a grid would have helped too, but whatever.
I feel like that would be too easy. I like you to have a challenge.
Yeah, she wanted to challenge me, and then I would have probably.
So when it says interpret the probability distribution, what is it? What am I asking? Or what is the question asking?
Well, it's asking me to figure out which is maybe the most likely. The most likely to occur is she would go to class 3 days a week, which would make me happy.
Could we maybe cuss and BS?
We could talk about some, yeah. And boy, did I really mess up too, didn't I?
Yeah, it's okay.
Yeah, anyway, I just realized that. We could talk about it being skewed and try to find the center, although I don't know how to do that off the top of my head right now. You're probably going to have to teach me that.
Oh, so we need to figure out how to find a mean when it's given as percentages?
Yeah, that's the thing. Yeah, I don't know how to find a mean. I mean, I could talk about the shape of being skewed, and I don't see any outliers. I don't know about the standard deviation either, the spread.
Yeah, it's tough because we need to be able to have more information, right? Yeah. Or we need to know more to be able to cuss and BS so that we can really do a good job interpreting this data. So we're actually going to circle back to that. But yeah, I mean, it is definitely skewed left, we could try to determine a mean, but these bars are crazy. It's nothing unusual, you know, and we could talk about spread, but we would need to talk about standard deviation. We could talk about range if we wanted to. So yeah, we've got some things we could talk about, but we need to learn more. We need to learn more. Okay. All right. So how about what? How about a cumulative frequency table? What is that? What does that mean?
That means as we go along, we add them up. So the first one would be 0.01. Okay. But sorry, that should be a 0. But when I get to this box right here, that's the probability of getting a 0 or a 1, getting both of those together. So I'm going to take the two numbers that are there and add them to get 0.05. We're getting like a running total. So there's a 5% chance that Nancy would attend class 0 or 1 day in a week. And then when I go to the next column, what was that? I was trying to change colors on you. When I go to this box, I want all 3 of these added together. So that would give us the total of 0, 1, or 2 days, and that would be 0.20. And then finally, the last one better add up to 1, because it's all of them together. And that's what we were saying. They have to total to 1.
Yeah.
And so Miss Young, much better job of graphing this than I did. So the first one would be like this. Okay. The second bar.
Well, we're going to do a cumulative relative frequency chart.
Okay.
And so we're going to do it's the line graph one. Do you remember?
Oh, that's the one where it's like here. And then goes up to here.
Yeah. This one doesn't go up very much at first.
Yeah. And then it goes up to here.
To 0.20. Yeah.
And then actually we go all the way up to 1. You need to go higher on your graph.
Yeah. So this one should end at 100% because by the end you should have accumulated all the probabilities.
Right.
So, and then connect the dots.
And then connect the dots, yeah.
Are you connecting him?
I'm connecting. You started and then I was, whoa, sorry, I can't draw a straight line to save my life.
So remember, like, when we talked about this, we said, you know, it's interesting, these cumulative relative frequencies, because you can tell like percentile and things like that from a cumulative relative frequency really easy. So just kind of remembering, I'm just kind of pulling back some language and some graphs that we saw early on in this course. Okay. All right, let's clear it and move on. Okay, wow. So let's say that X is the
almost like I knew what was going on.
Yeah. So let's say X is the number of courses for which a randomly selected student at a certain university is registered. So our variable could be 1, 2, 3, 4, 5, 6, or 7. Okay. What is the probability that X is equal to 4? So what is the probability that this certain student or these selected student is taking exactly 4 courses?
Well, and this is what I was saying earlier, where one's missing and you have to figure it out. So I'm going to take all of those probabilities that are given and subtract them from 1. And I'm hoping you have that all worked out because I don't.
Yeah. So if I do add and get 0.05 and then add and get, 0.14, 54, 64, 70, 75, then what's left over is 0.25. So remember, when I add them up, I have to get 1. So that means this missing guy right here is 0.25. That is what it is if it's exactly 4. What is the probability that this student is taking less than 4?
Well, then I would take the ones that are below it, the 0.2, the 0.3, 0.02, 0.03, and 0.09, and add them up.
And I would get
And
0.14.
yes, which you had already done.
Yep. And then, my bad, because it didn't get animated. What is the probability of less than or equal to 4? So this is the difference between 0, 1, or 2, excuse me, this is the difference between 1, 2, or 3 courses and 1, 2, 3, or 4 courses. So the equal to means included, which I'm sure you all know. So
Yep.
what is the probability that the student is registered for at least 5 classes? At least 5. What does that mean?
At least 5, that means 5, well, it would be the complement of what you just had there. There'd be 5, 6, or 7. So I could add up those ones or take the one she just did away from 1 and get 0.61.
Yeah. And then just out of curiosity, because this is a little different, why does this distribution not include 0 like the other ones?
Well, I mean, if you're not taking any courses, if you're taking 0 courses, you're really like not a student. You're just weird and hanging out on a college campus, and probably not.
Yeah. Okay. So the following histogram shows the relative frequencies of the heights recorded to the nearest inch of a population of women. The mean of the population is 64.97 inches, and the standard deviation is 2.66 inches. So this is a relative frequency distribution of a population of women. One woman from the population will be selected at random. Based on the histogram, what is the probability that the selected woman will have a height of at least 67 inches? You are so rude.
Okay, at least 67. That means we want the ones that are 67 or higher. So we want to take all of these people and add them up.
Yeah.
And there's
So,
no, you do the math.
yeah.
Thank you.
Yeah, just if it's at least 67 inches, then it's 67, 68, 69, you know, obviously. And then you just add the probabilities. So the graph is really nice, especially when the probabilities are given, because you're literally just adding probabilities that match whatever's been asked in the problem, okay? What is the area of the bar corresponding to a height of 67 inches in the graph? And what does this area represent in terms of probability?
Let's see, the area of the bar corresponds to the height of 67. So we want the 0.11, right? We want just the bar for 67.
Yep.
And that means there is an 11% chance or a 0.11 probability of a randomly selected woman from this population being 67 inches tall.
So what's the area?
0.11.
How do you know?
It's one wide. It's one wide. The bar is one wide, and it's make me a little calculus.
A little calculus. So yeah, like the bar, the base of the bar is only 1 unit, and then the height of the bar is 0.11, and this is just a rectangle, so base times height is 0.11. So the area of that histogram bar is 0.11, which is the probability of selecting a woman who's 67 inches tall, okay? And I say that because I really would like to bring it back, and I want you to remember how a normal model works. So let's say the histogram, we have the information for the histogram. Height is often considered a continuous variable because it's measurable. So you can have all heights in between, like it's not discrete, so it's not countable. And height often follows a normal distribution. Okay, so let's consider a normal distribution that uses the mean and standard deviation for the women as parameters. the mean of the population is 64.97 inches, and the standard deviation is 2.66 inches. Remember, mean gets inches and standard deviation gets inches. They stay in unit in the problem. Okay, so use a normal model and the relationship between area and relative frequency to find the probability that the randomly selected woman will have a height of 67 inches. How do I do that, Mr. Robbie? Do you want to remind them how you use normal distribution in that way?
We'd have to do the normal CDF thing that we on the calculator. Sorry, my dogs are barking out there. And we could go take the ones that are below 67 away from one, or it could do 67 dot. I don't have the calculator open, but do you need me to, you want?
No. Yeah,
Okay.
I think it's fine. Guys, remember the function is called normal CDF. So
Yeah.
you use the normal CDF function with a mean of 64.97 and a standard deviation 2.66.
And we posted the videos for the calculator tutorials. I think I did a video months ago about that. If you don't remember or are struggling to do that, come see us in office hours. We'll walk you through how to do normal CDF. But that's a calculator function to do that.
Yeah. So remember, because we're talking about heights of at least 67 inches, your lower bound is 67 and your upper bound is all those nines, right? You want it to go forever. Your probability that you get is 0.2236. That's what the calculator will give you, okay? Does it match what we got previously? Well, let's back it up. So earlier when we did this, when we said at least 67 inches with the probability on our histogram, we got 0.27. So same question, different method, 0.27 versus 0.2236. Why is there a difference there if we say, okay, well, height is generally normally distributed?
Well, you don't, because your bars aren't continuous, I guess. Is that why you're not?
Yeah, so the probability of 0.2236 is a little less because there's a little less area in the tail of a normal curve than in this particular histogram.
Okay.
Like if you think about your normal distribution and how that outside of 2 standard deviation works, this histogram doesn't quite match that, but it's pretty close. Remember that stats is it's an ish math.
That's why we say it's approximately normal.
Yeah, exactly right.
You learn that phrase.
Yeah. So just really quick, the probability that a selected woman has a height equal to 63 inches is an example of a probability that can be found on a discrete model, okay, like the height of a bar. However, there's no area of a single number on the curve. And so you don't really want to do like normal PDF, which is a function in your calculator where you're looking at a point distribution because of that continuous concept.
Yeah, you're going to be always looking for ranges of values on your calculator.
Right. So just kind of keeping that in mind that, depending on what you're looking for, a discrete model is sometimes better and a continuous model is sometimes better. So, all right, really quick, because this is part of your con homework and we just talked about it a little bit, but remember from way back when we talked about the normal curve, we said this is what's considered a density curve, and we're looking for the area under the density curve. So if this is a density curve, what's the probability that X is going to be less than 3? What does that look like, Mr. Bobby? What is that shape?
That would be, I'm going to try to draw that. This is 3 right here, right? And I want the stuff that's less than that. That would be all this junk down here.
Right. So in this case, I would literally be finding the area of a triangle.
I can do that.
You can?
I have to Google it, but I bet I can figure it out.
So what is the base?
It's all about the base. No, you go Google how to find a triangle. I'm not telling them how to find a triangle.
What is the base?
It's all about the base. The base is on the
I'm
bottom.
with you. So you got a base of 3 and you've got a height of 0.4. And you're going to divide that by 2. Is that right?
Yeah.
You feel good about that?
That 4 is a little skinny. You got, put it on a diet or something.
And then guys, that's it. That is this whole section seems more complicated than it is. Remember that when we talk about the probability using a density curve, it's literally just the area underneath the curve. Okay, so this is just a side note on this random assignment in here, is that probability associated with a random variable that's being graphed is just the area underneath, whether that's a histogram and you're talking about the bars, or it's a triangle, or whatever it looks like, okay? It's just the area underneath the curve. Okay, so you have 3 assignments to work on tonight. Your probabilities with discrete random variables, your probabilities in density curves, which is what I just showed you, and then your probability in normal density curves, which is you're going to need your calculator for, okay? So this is probably tables, and this one I just showed you, and then this one is your normal CDF, okay? Good luck. Thanks for hanging out with us, and we'll see you on the next video. Bye.
Bye.